Okay, let's go through, and feel free to ask questions because I don't intend to cover a whole lot of research except just to get an overview of the introduction, overview of the group. Because you've already seen some of the research topics that actually our group works on, right? Mohammed talked about genome analysis. That's a huge direction in the group, and both from software and hardware aspects. Juan talked about memory-centric computing in memory processing. That's another huge area in the group. I talked about RowHammer and DRAM. That's another huge area. So you've already been exposed to actually 3 major areas, and in a way that's better than what I can do in one single lecture. But I'm going to talk about some other things. Well, I'm going to skip some of these things because these slides were used for a different purpose. So hopefully everybody knows me. Feel free to ask questions. And you may have seen this picture if you've taken DDCA. I like this. One of your colleagues in DDCA is very good at art, so she made this. You can probably buy it for some amount, but I asked her for permission. Okay, and then another one. And you can find the links. Anyway, basically, I think Mohammed also mentioned this in an earlier lecture, but this is what we do in Safari. Our goal is to build fundamentally better computers and systems in general. And computers is very general, right? It's not hardware, it's not software, it's computers, right? In the end, hardware and software, there are a lot of trade-offs in the hardware-software space, so it's good not to divide people into hardware versus software, in my opinion. But it's good to know if you know everything, right? If you try to do system design across the stack. And we focus on computer architecture, hardware, software, co-design, systems, bioinformatics, and security. And who knows what else. So as a researcher, I think it's important to keep your mind open and be opportunistic, right? That's a good thing to do. So these are some, I think, incomplete, but some key problems that we see in computer architecture, computer systems, computing today. How do you make things more secure, more reliable, more safe? We talked about that with a specific study of RowHammer last time, but there's also a lot of other interesting issues in security, reliability, safety. So we actually look a lot into this. Again, I will not go into a lot of detail, but this is a major direction in the group. So there could be vulnerabilities, especially hardware vulnerabilities are quite interesting in my opinion, in memory, storage, and processors, because these are hard to patch, if you will. Software vulnerabilities are also interesting, but a lot of them are, let's say, preventable in software, whereas hardware vulnerabilities, if you actually have them, you need to change something in hardware. And how do you design something fundamentally trustworthy is a very difficult question, I think. Your circuits need to be trustworthy and side channel free, for example, right? People figured out ways of using side channels and processors to extract secret keys. Right? If you lose your secret key, all of your cryptography protocols are useless, basically. This is why hardware is so important, I think, in terms of security, right? Your trust is built on the fact that you cannot expose a secret key to someone. But if someone figures that out using side channel analysis, like power analysis or some other side channels that exist in the processors, or RowHammer, actually people have shown that, basically different types of vulnerabilities, then your trust is broken. There's something on chat, but I think I looked at it already. There's someone asking questions. Maybe you guys can.
I just can hear.
Okay, I can hear us. That's good. Okay, and then, I mean, we talked about RowHammer as an example, but there's a broader area over there. And then fundamentally energy efficient architecture. This is, I think, very important to look into. How do we design architectures to consume as minimal energy as possible, while also not hampering computation, right? I think memory-centric architectures we've been discussing in earlier lectures is a key example of this. Certainly we discussed processing near memory and processing using memory as 2 types of processing in memory, right? And I think these are really fundamental. I've seen a lot of terminology in memory processing, and what's really fundamental is the distinction between these two. It's not fundamental that you do the processing inside the chip or outside the chip, or near or somewhere near the chip. What's really fundamental is, do you add logic to do the computation, and where does that logic sit? Is it near the memory? Today, basically, you have processor here, memory here. Get the processor closer and closer and closer and closer to memory. It could be inside the memory chip, it could be near the bank, whatever. But as long as you add logic, that's processing near memory, or logic near memory. This is very fundamental, I think. In a sense, it's very similar to the current model, right? You have the processor far away, you just put it closer. And the processor could be an accelerator, subset of the accelerator, subset of the ISA. It could be a GPU, it could be a CPU, it could be an FPGA. It's the same, basically. Processing gets close to the logic. close to memory. But the other part is what we call processing using memory. And I think that's fundamentally different from the first one. Basically, you have processor memory, you forget about the processor, right? Like you just have memory. Now, this memory device can do computation, as Juan mentioned, right? In Ambit, for example. And that memory device has some analog operational properties that enable it to do computation. And we do a lot of work in that area. And this is very fundamentally different because you don't actually add any logic. Of course, you can combine these two paradigms. You can add some logic plus exploit the memory's computation capability, which I think should happen also going into the future. But that processing using memory is also very interesting and fundamentally more efficient because you don't add any logic to the computation. The question is, of course, at what things is this fundamentally more efficient and how do you make sure it works? So there are a lot of issues over here, right? And you guys remember the processing in memory lecture or memory-centric computing lecture. So now you have a good idea of this direction also. And feel free to ask questions also. So I'm assuming you remember it from the lecture. So we're looking onto low latency and predictable architectures. It's actually really important, I think. Oh, before I go into it, I think, for example, this processing near memory and using memory, you can do this in all memory devices. And I'm actually quite interested in many different devices. DRAM, we've been talking about it a lot. But there's storage, SSDs, there's emerging memory technologies, and all of them have the capability to do processing using memory, some analog computation capability. And it's really good to look at how to do that and how to exploit it for applications and how to make it easily programmable. So Juan mentioned the SIMD-RAM, for example. I don't remember if anyone selected that this time, but we discussed in seminars, past incarnations of the seminar. So that that takes a step towards more programmability of this analog computation in memory. And again, as I said, fundamentally energy efficient. So memory-centric architectures improve performance, energy efficiency, both of them at the same time. But energy efficiency is really key, in my opinion, because people try to improve performance in many different ways. But it's very difficult to improve energy efficiency and performance if you make the system complicated. And I think memory-centric architectures take us towards a direction where fundamentally the computation is very efficient because you don't move the data and you exploit the analog computation characteristics. And then how do you actually make it very high performance also becomes interesting. So there are a lot of interesting things over here. Memory is also very parallel, right? You have, imagine this petabytes of memory. If actually all of the cells are doing computation at the same time, that parallelism is much larger than what parallelism you have in the processors today. Just because of the sheer amount of memory that we have, right? If you actually look at the transistor counts, I think I've shown this in a DDCA lecture this semester, but in a huge supercomputer, more than 97 or 98% of the transistors are dedicated to memory. I don't believe this number includes storage, but memory, DRAM, for example, because it's much denser, right? Memory is much denser. So low latency and predictability, these are actually quite important topics. We have been doing a lot of memory controller research to reduce latency, to make things more predictable. I think these are very important going into the future. And the difference between them, even though I couple them into two areas, I think these two are very different things actually. Low latency means you should get the result fast, right? Predictable means you don't care how fast, as long as you can predict when you're going to get the result. My favorite example is the tram or train schedules. If you've taken EDCA, you remember this example probably. I don't care if the tram is fast. I care if the tram leaves at the time it promises to leave. If the tram is fast, it leaves 2 minutes earlier and I'm not there. So I miss it. But if the tram leaves at the time it promises, then it's predictable and I can plan around it. So that's the difference between these two things. And think about it. So quality of service is very different from latency in general. Of course, if the promise is it's very latency, high latency, low latency and high throughput, you should satisfy it while not destroying the predictability. In existing architecture, there's a lot of research sharing. So predictability becomes a problem because you're running a lot of programs, for example. How do you predict? How do you guarantee that the execution time of a program that you promised to someone? Or if you're running a cloud server, for example, how do you guarantee that a person's program is not going to be destroyed by another person's program because you're running them concurrently for efficiency reasons, right? So these are actually really interesting things that are going on also in the broader field. And then we talked a lot about architectures for genomics, but we also do research and architectures for machine learning and broader medicine and health. And I think specifically in this machine learning part, we also do a lot of work on using machine learning to improve architectures. So for example, how do you design a memory controller that makes better decisions in hardware? So we've been working on reinforcement learning based memory controllers, for example, prefetchers that use reinforcement learning or neural networks. More recently, I think we had a paper at Micro. The idea was basically, Rahul drove this idea. If he was there, he could give a lecture also on that. But basically, the idea is to predict which load requests are going to miss in the on-chip cache hierarchy, so that you can actually start the request early. So if you think about today's on-chip cache hierarchies, you have the L1, L2, L3, L4 caches. They're huge. And it takes a long time to query those caches, around 50 cycles or so, maybe more in the future. Can we somehow predict that a load is not going to find its data in any of those caches so that we can start the memory access, main memory access earlier? And Rahul designed a mechanism called Hermes that uses perceptrons, which is a very simple model of neurons that were developed in the 1950s, to do this prediction. It's a Micro 2022 paper. It won the best paper award, actually. You can find it online. Again, I'm not going to go through all of these, but if people are interested, is it going to be presented in this lecture, in this seminar? Can take a look, perhaps. I don't remember. I think multiple people expressed interest, but I don't remember if you selected that paper in the end. So basically, how do you improve the decision-making that's going on in the architecture is a very important thing. So people have used a lot of heuristics so far. Can we make it more robust using machine learning techniques is becoming very interesting. Similarly, we had one work last year, again, ISCA, it's called Sybil. There, the idea was to use reinforcement learning to decide which data should be placed in what kind of SSD to maximize performance and energy consumption. It's not, okay. Okay, so you're going to see it in some other way, perhaps. Okay, so basically, this is another area that is very important, and I'm going to get back to that also. I mean, I think we mentioned this earlier, but we usually take a very broad view of computer architecture and look at algorithms through devices as much as possible. For example, in the processing using memory work, devices or circuits have some capability to do analog computation. How do you change the algorithm to take advantage of that analog computation? I think that's a great example of algorithms through devices, because that analog computation is fundamentally different from what we do. It's basically bitwise, block bitwise analog computation you do. You can operate using majority operations or block bitwise ANDs or ORs or NOTs on 8 kilobytes of data, let's say, within a single subarray. And if you can do that on millions of bytes of data in parallel, how do you change the algorithm actually to take advantage of this? It's possible to do that. So that's an example. Okay. And similarly, you can actually apply that to bioinformatics workloads, for example, right? How do you take advantage of processing using memory for bioinformatics or processing near memory for bioinformatics? Okay, I think Mohammed discussed this, I think, and you've seen examples of this, like the work we do in genome analysis. Acceleration is an example of this expanded view. Specialization, machine learning is another example of that view. Processing in memory is also another example of that view, I would say, because it really disrupts the entire stack. Okay. And we also examine ideas. So ideas are the most important thing in progress, I would say, in scientific progress. You come up with an idea, it may not be easily implementable, but you basically look at how to make it work over time. And that's, in my opinion, that's a very good kind of research. That's a spark, basically. You generate a spark, and then you basically explore how that spark affects things, right? So with, again, I'll pick processing using memory as an example, but you have this idea of multiple row activation, and if you do it concurrently, what kind of benefits do you get? It basically opens up a whole world of opportunities after that. Okay, so this is a very busy slide that talks about maybe in more detail what we do. So I think I'll go through these relatively quickly, but we're very interested in emerging non-volatile memory technologies like phase change memory, RRAM, unifying memory and storage using a single interface so that you can get rid of a lot of inefficiency in data management in existing systems. if you look at existing systems, you have memory, storage, they're managed completely differently, right? You have to move the data between storage to memory and storage. Can you actually have a single unified view of memory and storage? And this could be possible with emerging technologies that enable fast access to large amounts of data in a non-volatile fashion. So one of the reasons why storage and memory evolve very differently over time is because of the devices. So DRAM is, for example, fast but volatile. When you power it off, you lose the data. Storage, SSDs today, but hard disks in the past. Well, still today, but hard disks still exist today because they actually have a very good cost point compared to SSDs. They are devices that are non-volatile. You plug off the power, the data still remains. So you can actually do manipulation of persistent data structures. But unfortunately, they're very slow compared to DRAM today. So if you have an emerging memory technology that's similarly fast as DRAM, but also non-volatile, now that enables opportunities that were not possible before. And this is something that we've been looking at for some time. I think there's more to do over here. I mean, I think I already said the low latency and predictable architectures. This is, I think Juan also mentioned in the data-centric architecture, we want low latency in architectures. If your goal is to design a data-centric system, data access should be low latency. So having high latency is not very good for if you're bottlenecked by data in the end. We talked about security, reliability, safety. So there's a lot of work going on here. Acceleration for machine learning, AI, genomics, health, medicine, etc. So there's a lot over here actually. Our work spans a lot of areas. It includes FPGAs, GPUs, specialized accelerators, also processing in memory, and how to take advantage of all of them together. So there's a lot of work to talk about here if you're interested. And then I think this is something that I mentioned earlier. How do you design data-driven architectures, machine learning driven architectures, controllers, and make them more intelligent? And then the data-aware architectures, this is something that we did not discuss as much, but basically the idea here is to, if you look at today's architectures, they don't communicate a lot of information about the semantic properties of data to the underlying hardware or the system. So if you look at data, it has a lot of properties, right? When I look at a piece of data, it has some security property. Usually it's not specified actually in the software. Even the software designer may not think about it. It has some privacy property actually. A lot of genomic data has a lot of privacy constraints on it. And even a lot of data has a lot of privacy constraints on it today, right? It has some property, a proximability property, meaning if you get bit flips on this data, there is some error tolerance you have. It has some compressibility property based on some compression algorithms work well, some compression algorithms don't work well. So it has a lot of properties, locality properties, potentially also how many times it's reused, given some access pattern. So all of these properties exist for data. Can we actually express these properties nicely to the architecture such that the architecture can take advantage of it, right? For example, if you're dealing with security critical data, can you actually ensure that security critical data doesn't get exposed to some other program using a sidechain? So that's why I think there's a lot of potential over here in terms of making the architectures more data characteristics aware. Can we express these characteristics to the underlying architecture, and the underlying architecture can use them to improve performance, energy, security, reliability, etc. So there's a lot of interesting work, in my opinion, in this area also. And we have some papers that were written in the past. In fact, Ataberk has presented a paper called Metasys, right, at High Peak earlier this year, that talks about, that basically presented a FPGA-based infrastructure that enables you to do real experiments using this sort of expressive memory architecture. That was a prototype. So initially, when we wrote the paper in 2018, it was basically simulation. Can we express the characteristics of data so that we can improve, for example, caching capabilities or prefetching capabilities or security capabilities or safety capabilities in the architecture? And Ataberk and Konstantinos and others designed an FPGA-based infrastructure to do that. Am I correct? Sure. Okay. I got the best paper award, by the way. Okay. Any questions? I'm giving you a broad overview. I mean, clearly there are a lot of papers that are associated with these. But this is something that we're looking at. I think at least some of the key principles can be summarized this way. We want to be more data-centric. And I think Juan had a slide on what it means to be data-centric, processing near data, processing as much as possible, having low latency, low energy access to data, making data storage as cheap as possible, but reliable also, having intelligent controllers, ensuring that data doesn't get corrupted. Those are all data-centric. Data-driven means that you basically design architectures to make intelligent decisions based on data, as opposed to human-driven. So a lot of architecture design and system design so far has been human-driven, right? Humans basically, okay, I design a cache. These are the characteristics that I want to add into the cache. These are the heuristics I add. Of course, humans use data to simulate what happens, but once you design the controller, it operates using some heuristics. The controller doesn't improve its policy based on its experience, right? It's very different from how an intelligent system operates. Whereas data-driven means you evaluate your policy as you get data and change your actions based on that, right? As humans, we do that, right? As humans are actually very data-driven beings, let's say. I mean, very simple things like touching a stove, right? If you're a kid, you touch a stove, you do it once, and if it was hot, you don't do it again. You quickly learn based on data. You're not hardwired with the heuristics that says touch the stove no matter what, right? But today we're hardwiring our machines with heuristics that are human-driven. So we want to break free out of those heuristics, essentially, so that we can actually make the architectures better over time. And data, where I just talked about, basically, can we express the properties of the data? And actually, this is not just about the data also, interestingly, because you don't want to express just the properties of data if you're thinking toward this direction. You also want to express the properties of computation, in my opinion. How critical is this piece of computation and maybe data associated with it for security, for example? You want to encapsulate these things that you want to compute so that with different characteristics. So how approximable is this computation? Again, everything I said kind of applies to that, right? Should you keep this computation private, let's say? So if you express these properties, you can design systems that can actually more fundamentally provide security guarantees, for example, as I said earlier. If this data needs to be secure, maybe execute it in isolation alone and don't execute anything else at the same time. There's a heavy-handed solution, of course, but that's one way of getting rid of these side channels. Okay. Yeah, so basically, I'm very interested in principles, and these are some of the principles that we have, especially in this data-centric, data-aware and data-driven parts, basically. You know, I don't know if I want to go over these. I mean, we work a lot with industry also, actually. Industry, we talk, we get input in terms of what problems they have. We don't necessarily do the research that they think is interesting, because sometimes they think very short-term. But longer term is more important. Their short-term problems are not that interesting, but their longer-term problems are very interesting, right? So, for example, in processing in memory, it's been a long road, right? As we have seen in the earlier memory-centric computing. So it takes time to open people's minds to some disruptive ideas, I would say. That was also RowHammer, like I mentioned last time. RowHammer, we did a lot of work, and finally industry is writing papers about it. In 2023. We started doing work in 2012. Our first paper was rejected in 2013 from Micro. So it would have been 10 years actually if it weren't rejected, but it got published in ISCA in 2014, and industry finally writes a paper about it in 2023. So you can see the timeline, right? There's a long timeline to actually get the industry moving. I mean, industry, of course, didn't stay silent. They actually implemented a lot of the solutions, some of which were proposed by by us inside their systems, but they were not fully secure, as you remember from last lecture, right? So there's a lot of impact to be had, I think, by understanding the industry's problems and solving them in a longer-term manner. You don't want to tweak the transistors to solve the short-term manner, right? You don't want to be designing products for industry. if you're doing research. Of course, if your goal is to design products for industry, then you should be doing products for industry. But that's not research, in my opinion. Unless there's an application. So applications change the thing, basically. If there's an application that's new, and if that requires a system design that's not done before, but it requires some understanding of the full system so that you can actually improve an application significantly. That's where I think that's still research, in my opinion. Okay, so this is one paper that we're not going to cover, but that talks about a lot of these principles more recently. Any questions? I'm staying at high level, but I'm going to give you a low level thing soon. I'm going to actually go from this high level to a very low level. I like doing that. Okay, but before I do that, I think Mohammed introduced the group, and we had some people in the group earlier in the first lecture over here, but this is my group. There are quite a few people right now. We actually have these newsletters, as you can see. This is pre-COVID. This is during COVID. This is, I wouldn't call it after COVID, but sometime around COVID again, December 2021. But we have newsletters. If you're interested, you can take a look at these newsletters for some interesting updates during the time frame of the newsletter. So we're going to release another one, actually. I keep promising it for 3 months. We have one, but it's just not released publicly. So it's microarchitectural right now. It's not exposed to the world. But it's going to be released soon. It's going to cover basically whatever happened since December 2021 and have another picture. So how many people are interested in pursuing a PhD here? If you're not already doing that. How many people are already doing it? Okay, of course, there are 2 people here who are shy. Joel is less shy. Okay, you're not interested? You don't know yet. Okay, even if you're not interested, it's good to know what PhDs do. These are my PhD students plus postdocs. It's not complete, I think, because I was adding stuff today. Well, PhD students are complete. I think postdocs are not complete. But you can also look at their theses. All of the theses are available online. Okay. Yeah, I mean, I think Mohammed covered some of these, so I will go through these relatively quickly. So if you're taking this course, Seminar in Computer Architecture, some of you probably took the Computer Architecture and the DDCA course, basically. These links are old, as you can see. There's a Spring 2023 edition that's going on right now. But if you're really interested in computer architecture, you may have taken this course, or you may not have taken it. I would recommend taking it. We're going to teach it this happens in every fall semester. And if you have not taken DDCA, and I know that some people have not taken DDCA because there are different streams of students coming into the seminar, I would recommend looking into this DDCA course because it gives a full introduction to, let's say, digital design and computer architecture. Okay, there are other courses, and you can find them online. These are some, again, not up-to-date links, but I mean, any edition is good. Let's say I change the course every semester in different ways. So the fall 2022 version is not the same, and fall 23 version is not going to be exactly the same. Okay, seminar is what you're taking right now. So we also have a crossing in memory course. This is the first crossing in memory course that I know of that anybody has started. Of course, anybody can correct me on that. So we actually have a lot of interesting things over here. If you're interested in processing in memory, for example, we have a genomics course that Mohammed mentioned. I think Mohammed mentioned all of these, but genomics courses specifically focused on genomics. Heterogeneous system course that Juan is leading. So these are courses that you can take online, basically. You don't need to register or get credit. You can actually find them online. A lot of people do that and send us emails. But I would recommend people who are interested to look at it because these cover some cutting edge topics, for example, on GPUs and also some FPGAs. A lot of the focus is on GPUs, but there are some FPGAs and other heterogeneous systems as well. Hardware, software, co-design. This is more, let's say, a course that's being developed over time. There's solid state drives that Mohammed and Rakesh are leading. Do I hear myself? Is everything okay on Zoom? Are people still awake on Zoom or are they bored?
No, it's all good.
Okay, good. Can you see me when I speak on Zoom? Or am I far away from the cameras?
If you're all the way to the left, you're out of the picture, but normally it's okay.
Can we move that while we're doing this? Because I like staying here. I'm still not used to this. During COVID, I was presenting from my computer most of the time. So you don't need this, right? You just keep clicking. So you can see that. That's another example of data-driven human beings, right? I received a lot of input data that changed how I actually interact with the computer also because of some environmental thing that's going on outside. So we have solid state drives course. Actually, this is important. We should really rename this to more storage systems course, I would say. And I think this is actually going to be even more important going into the future. Like we talk a lot about memory, and memory is very important clearly, but storage is actually perhaps even more important in many applications going into the future because memory is of limited size, whereas storage can store a lot more, right? There's a lot more possibility to manipulate data and be more efficient. And also storage is here, memory is here. If you want to do memory processing, either you get rid of storage and bring everything into the memory directly, or you move stuff from storage and memory. And that actually is very inefficient. Moving data from storage to memory is actually quite inefficient today in terms of both performance and energy. So going into the future, storage is going to be even more important in my opinion. Yeah, these are things that people don't talk about in general, but if you look down maybe 20 years down the road, I will bet that storage is going to be important. Maybe we will think more about storage as a computing device as opposed to memory or processors. Okay, and then we have specialized courses on the DRAM exploration, RowHammer also, and Remulator. This is more on the simulation aspects. Okay, any questions? These are courses. I mean, I talk about courses because courses actually are feeding the research also. I'll have a slide on that soon. Yeah, I think you may have seen. If you're interested in knowing more, there's more detail over here, especially on what it is like to be a PhD student, do research in these areas. I have this talk that they invited me to do at the architecture mentoring workshop, undergraduate mentoring workshop, a couple of years ago at the major architectural conference, and you can take a look at it. I don't have time to do that. I mean, I could do it, but I have other things in mind in the agenda for today. Okay, there's also more if you want to learn more about what we do and some things interesting. Yeah, this is why we focus on courses, because I think this is an endless loop, if you will, because in the end, research and teaching are very similar, in my opinion, at least in the end result, right? You do research. Why do you do research? You do research to educate the community. What do you educate the community? Community, scientific community, and hopefully at some point the broader community. You educate the community. What do you educate the community on? Basically, it's something that no one has known yet. That's the research. No one has done it. You did it, and you educate the community. You do some teaching to basically tell what you found out. Right? Teaching is essentially the same thing, except you tell people what everybody could know. So that's the, let's say, minor but critical difference between research and teaching. And these two things are actually really important because they feed each other in the end. What was research 10 years ago becomes teaching after it's known. Right? So a lot of the things that we discussed in this course are kind of education, right? You're not doing research, you're studying what someone else did. Okay, so that's why I think it's really important to have research in even the beginning courses at a university. Otherwise, I mean, I think the university environment does both in the end, right? My goal as a professor is to do research, education, and service in the end. And but if in the education, if research is missing, there's something missing that the students don't get exposed to. If we do that, that's why I think research is very important to inject into the teaching as well, because that enables those students to get the sparks that I mentioned earlier, right? If you actually injected the ideas early, oh, you can actually do things differently. People are working on this research, and you can think about it. Maybe that can enable a spark. I don't know when. Maybe 2 minutes later, maybe 2 hours later, maybe 2 days later, 2 years, maybe 2 lifetimes later. I don't know. But yeah, that's what happens. Okay, so you can see more talks also. I mean, you probably have seen our open source stuff. I'm not going to harp on that. Actually, this is what I wanted to mention. This is an old slide, but we do these Safari live seminars. Well, right now they're hybrid. We started during COVID, that's why it's live. But we have these computing related seminars that we host, and there will be some seminars this semester also. So we will invite you to those as well. If you're interested in the topic, you can attend, ask questions, etc. Does that sound good? I believe there are that are scheduled or being scheduled right now for this semester. And again, there are a lot of interesting things that, for example, in-memory processing is actually a huge area today. And we had a special session last year in this symposium that essentially covered a lot of aspects of in-memory processing. If you're interested in this stuff, basically, you can find a lot of information on our website and channel, etc. Again, I don't have time to go over this. Different people talk about different things over here. So open source, I think we believe a lot in open source. I think this is really important for progress in general. As much as possible, we try to open source things. I will give a story about that later on when I go into the more depth, let's say. And you can find a lot of these open source artifacts online on our GitHub. So a lot of these tools actually are being used by academia and industry. So Emulator is one example. It's a state-of-the-art simulation system for memory systems, and we're going to release a new version of it also. So it's actually being used by industry and academia. So we actually receive a lot of feedback privately from industry as to what to put, what to improve, and it's all good, constructive. It's open source basically. It's released under the MIT, which is the most free license that you can find today. So this enables a lot of, I think, let's say, research and development happening across the world as well. So this is another example. I think Juan mentioned this. These are processing in memory benchmarks for the UpMem system. It's being used by a lot of people also right now. This is the SSD simulator that we developed, MQSim. And you know about RowHammer. This was the code that we released when we wrote the paper. And then Google actually used this code to release their own code. So there's a Google thing as well. And then there are a bunch of other things. SoftMC we talked about also actually when we talked about RowHammer, right? This is the DRAM infrastructure that we built. It was built in 2011, but we released in 2017. So you can see that we don't necessarily release things right away. And there's a good reason for that. I will discuss that later on. So there's 6 years. And actually a new version of it, Ataberk is responsible for it. It's also online. It's also online, yes. And it's, yeah, the paper is also online. You're probably going to update the archive paper also. So, yeah. Yeah, basically, these things evolve also and people use it. So SoftMC, for example, enabled a lot of research on figuring out how DRAM operates by us as well as many others in the field. Okay, so there's more. So we do a lot of open sourcing, basically, including the lectures and yeah, and courses, everything in the courses. Any questions? Yes, please.
I think that most of those tools have been developed using A or C or C++ as a programming language.
Yeah.
Are there actually any factors that affected this decision other than like performance and hardware architectures?
Yeah, that's a good question, basically. I mean, not all of them, but most of them are C or C++. You're right, at least the ones that go over here. Well, I think performance is one of the major reasons, right? Because if you want to write a simulator, you really want it to be high performance. And it's very hard to get high performance with much higher level languages today, like Python, Java. Actually, the first version of Ramulator that I wrote together with my colleague at Microsoft Research, this is circa 2007, 2006 actually, not so. It was C#. Why? Because Microsoft, you can use C# and you have a lot of tools, right? So it was a little bit higher level. In the end, C# is a higher level language. A lot of things are similar to C, of course, but still higher level. So we wrote it in C# and we never translated into C or C++ until I gave that simulator to my students at Carnegie Mellon, and they said, okay. Actually, initially we were using C# also, but then it became very cumbersome to continue with C#. It was slow. The compatibility with other tools were not that good also. So we decided to switch to C and C++. So there is a version of, I believe there's a version of Ramulator that's C# that's also released. Not as popular as this one. Yeah. But I think it depends in the end. So for example, I think in DRAM vendor, there's a lot of Python also, right?
Yes.
In this current release.
Around
For the what word?
Yeah. It's a vector around the C++ API.
Yeah, exactly. So you could actually program it using Python also if you want simplicity.
And R as languages, but they're also used a lot of such kind of
Could you say it again?
Are assembler languages still used to log such time?
I wouldn't say assembly. I don't see a lot of benefit to assembly, but I mean, certainly lower level things like hardware description language is very low. SoftMC has a lot of very low code, right? Because that's what we program the FPGA with. But yeah, we don't do a lot of assembly, I would say. Okay, are you going to correct me or?
No, that's
Yeah.
much great.
Yeah, there's not much.
There's RowHammer where you could find some.
That's true, yeah. Yeah, I mean, RowHammer, yeah, that has some assembly, but because we demonstrated using that assembly code that I showed you last week. Yeah, but it's mainly for demonstration purposes, not to, because it's very cumbersome to program a huge simulator assembly. And you can do a lot of things in C. I mean, C has ways of actually incorporating assembly into it. If you really want something to be performance critical, you can actually call some assembly commands in C. That's how low level it is. Look, any other questions? Okay. So this is a very quick overview. I'm not going to talk much, basically. So these are some key problems that I see, I think, that we're having going into the future. Sustainability being a very important one. This we've talked about. Workloads are becoming more demanding, and there are new device technologies that are happening. So if you've taken DDCA, I talk about this as there's a lot of opportunity at the top, meaning top of the software stack, workloads, algorithms, etc., architectures, and there's a lot of opportunity at the bottom also, new technologies and how to enable them. I don't have the slides right now. I could probably find them, but I'm not going to do that right now. But these are some directions that are actually feeding into our research. Just to give you a little bit more insight, I mean, our group is relatively big. It's more than 40 people, but those 40 people include PhD students, postdocs, master's students, bachelor's thesis students, semester project students, and also interns that we take from all over the world. So it's a big group, and there's a lot going on. It's very hard to summarize everything in a single presentation, but what we do, let's say weekly, gives an idea of the kind of major research areas that are going on, right? For example, processing in memory has some meetings. Should really have more meetings, I think. This AI/ML is a general topic on how do we accelerate machine learning? How do we make it more scalable, more robust? And also how do we use machine learning to design better architectures, data-driven, as we discussed. Storage, I mentioned that. DRAM, I mentioned that. So a lot of the RowHammer research gets discussed in DRAM, but also other types of DRAM research gets discussed over there. There's bioinformatics, as you can see. And then there's an emerging technologies and applications meeting. Some of these actually overlap in terms of topics with different meetings, so different, and anybody can attend any of the meetings. And some people attend multiple of these meetings, which is a good thing, because you get exposed to a lot of different ideas. These are research meetings as well as brainstorming meetings. People discuss papers, ideas. Sometimes it's actually very similar to what we're going to do in this course. Somebody presents a paper, and there's a lot of discussion on that paper, and people brainstorm ideas to actually, oh, can you do this? Or maybe there's something wrong in this paper, and we could do better, or something like that, right? And then there's and these topics evolve also. If I showed you this picture, let's say 5 years ago, the names would be very different. If I showed you this picture 10 years ago, the names would be very different. I'm sure I can dig up my records and slides to figure those out, but I'm not sure if it's going to be the most useful use of my time to do so. Yeah, there's a meeting on hardware, software, co-design, and security in general, because these things are very closely related, as I just told you about the Metasys paper that Ataberk presented, right? That paper basically shows that by expressing things better in the hardware-software interface, you can do better memory safety on real FPGA prototypes. And we have a reading group, which is actually kind of similar to this, except we normally cover multiple papers. That's where all group members attend. And then we have a general group meeting. That's usually on administrative issues, but sometimes on research also. So you can see now how some more insight into what may go on in a research group, right? There's also meetings with industry. Some of them are regular, some of them are on demand. These are less frequent, of course. These are more to either get feedback from industry, or this is what we have done, what do you think? Can you use it for something? Or to get ideas from industry in the sense that what are the interesting problems that you may it may be useful to potentially look at. Okay, and we get a lot of funding also. We should get more funding. But I know you guys are not from industry, but it's really important, I think. I think this is something that's going to be important for future in the world, I think. How do you get the funding to do fundamental research? I see this being threatened by, let's say, a lot of politics. I should say it that way, probably. But basically, fundamental research is the amount of funding that goes into truly fundamental research is reducing in the world. But we need fundamental research, right? Not everything can be application oriented. There's a huge hype today, clearly, on machine learning that you may know, ChatGPT, etc. But not everything in the world is that. Right? There's a lot of fundamental things that we really need to develop for other things. Like extremely efficient computing, right? How do you make things more sustainable? I mean, how do you design power systems that are going to sustain things much more efficiently, right? These are fundamental, but they may not be as flashy as ChatGPT. So there's a huge danger I see that world is moving towards this. Oh, okay, let's do the flashy thing and ignore all of the areas. I'm much of a believer in fundamental things and more, let's say, more reasonable distribution of resources for research. 10 years down the road, if no one is able to design that, I don't know, transformer, what are you going to do? ChatGPT is not going to help you, probably. Well, you can say, okay, robots are going to design it. Are you going to trust them? I think that makes my point. Okay. Okay, that finishes the introduction. Any questions?